Hello, we at the Mr. CFD Group are honored to present you with training services. In this training chapter, we aim to introduce the battery model in ANSYS Fluent software. Please stay with us. In the first step, we present a general introduction to the battery. A battery is a source of electric power for powering electrical devices. In other words, a battery is a device for converting chemical energy into electric energy if needed. This energy conversion from chemical into electrical occurs through chemical reactions. In recent decades, batteries have been considered the most efficient device for storing electrical energy used in industry. Hence, batteries have many industrial applications, from electric appliances and electronic devices to hybrid electric vehicles, called HEVs, and electric vehicles, called EVs. In battery construction, the main component is the battery cell, which supplies electric energy. A battery cell consists of a negative electrode, a positive electrode, and an electrolyte layer. This battery cell is placed inside a metal or plastic casing for insulation and safety. On the outer casing, there are two terminals, including the positive and negative tabs, which connect to the internal electrodes. We assume that a battery is connected to an electrical load through an external electrical circuit. Electrochemical reactions occur within the electrolyte and electrodes. As a result of these reactions, positive ions are formed and electrons are released. Positive ions conduct through the electrolyte and transfer to the positive electrode. And the released electrons transfer to the negative electrode and conduct through the external electric circuit. The main concerns when designing a battery include battery's performance, life, and safety. Therefore, battery models in ANSYS Fluent allow simulation of the battery cell using CFD technology to study their thermal and electrochemical behavior. In ANSYS Fluent software, the battery model is one of the crucial capabilities for users. We want to discuss the concepts of battery modeling. In battery simulation, the battery is regarded as a homogeneous body. In other words, the computational domain does not need to include all layers present in the battery. The zones have to be identified in the computational domain, including the cell, tab, and busbar. Battery cells are known as active components. Active zones are the components of the battery where electrochemical reactions occur. Tabs and busbars are known as passive components. Passive zones are components of the battery that do not directly participate in electrochemical reactions, but only conduct electrical current. Battery tabs, or terminals, are the positive and negative connectors that carry the cell's electric current. Busbars are only used for battery pack cases because they connect multiple battery cells. The battery model in ANSYS Fluent mainly focuses on conducting thermal analysis of batteries. In simple words, significant heat is generated during a normal battery operation. So considering that the battery operates based on electrochemical reactions, a coupled thermal electrochemical simulation is used to compute the heat generation rate. In other words, the thermal and electrochemical behaviors of a battery are coupled. So, depending on how the thermal and electrochemical behaviors are coupled, 4 different solution methods are available in Fluent software. CHT coupling method, FMU-CHT coupling method, circuit network solution method, and MSMD solution method. First, we refer to the CHT coupling method, derived from conjugate heat transfer. CHT is considered the simplest solution method. We assume that we already know the heat generation rate during battery operation. So in the thermal analysis, we determine the heat source term in the energy equation explicitly and directly. According to the CHT approach, this energy equation is solved. A single potential equation is solved in the passive zones to obtain the Joule heating. Next, we refer to the CHT FMU coupling method, derived from the functional mockup unit. This method allows users to use their own electrochemical model. These can be imported to Fluent software through FMUs. The sets of equations solved based on the CHT-FMU method are similar to the CHT method. Next, we refer to the circuit network solution method. According to this approach, we assume that each battery is treated as an electric circuit. So if we have a battery pack, we assume that the battery pack is treated as a network circuit. Finally, we refer to the MSMD solution method, derived from the multi-scale and multi-domain nature of batteries. Generally, modeling lithium-ion batteries is difficult due to their multi-scale and multi-physics nature. Therefore, the MSMD battery model is a comprehensive method for modeling lithium-ion batteries. For the MSMD approach, the differential equations involving the battery's thermal and electrical fields in the computational domain are solved. First, we present the energy equation that solves the thermal field. We introduce the potential equations that solve the potential field in the positive and negative electrodes. Several electrochemical submodels are available in Fluent software to determine how these source terms are computed. The NTGK model, ECM model, and Newman's P2D model. First, we refer to the NTGK electrochemical model. This simple semi-empirical model is proposed by Newman, Tiedemann, Gu, and Kim. The NTGK model is used to simulate the charge and discharge cycles of the battery for a condition where the electric load does not change much. In the NTGK model formulation, the volumetric current transfer rate in the potential equation is computed as shown. The model parameters are U and Y, which are functions of the battery's depth of discharge called DOD. Depth of discharge, or DOD, indicates the ratio of the used capacity to the total capacity of the battery. According to the relation shown, during the discharge process, the battery's discharge percentage increases over time. So DOD is always between 0 and 1. 0 indicates full charge and 1 indicates full discharge of the battery. Therefore, the battery models Y and U can be fitted from testing data as a function of DOD and temperature. According to these relations, we need to determine the coefficients A0 to A5, B0 to B5, and C1 and C2. After JECH, we study Q.ECH in NTGK formulation. So the heat generation rate due to electrochemical reactions in the energy equation is computed as shown. Next, we refer to the ECM electrochemical model. This semi-empirical model is derived from the equivalent circuit model. The ECM model is economical and versatile, and it can be used for different types of solid batteries, not only lithium-ion batteries. In addition, unlike the NTGK model, it is suitable for simulating the battery for conditions, including abrupt fluctuations in the electric load. According to the ECM approach, the electric behavior of the battery is mimicked by an electrical circuit. In other words, we assume that a battery system is equivalent to an electric circuit to use the relations of the electric circuit for the electrochemical calculations of the battery. Here, a set of equations governing the electric circuit are shown. By solving the electric circuit equations, the voltage-current relation is obtained. Note that for a given battery, the open circuit voltage, the resistance of the resistors, and the capacitance of the capacitors are a function of the state of charge, called SOC. The state of charge, or SOC, indicates the ratio of the available capacity to the total capacity of the battery. It means when the battery is being charged, it is the percentage of energy stored in the battery to the total capacity. So SOC is always between 0 and 1. 1 indicates a full charge, and 0 indicates a full discharge of the battery. There are 3 methods available in Fluent to determine functions of open circuit voltage, resistors resistance, and capacitors capacitance, including the 5th-order polynomial form, Chen's function form, and 2D table. First, the 5th-order polynomial form, where open circuit voltages, resistances, and capacitances are only functions of SOC. Coefficients A0 to A5 for RS, coefficients B0 to B5 for R1, coefficients C0 to C5 for C1, coefficients D0 to D5 for R2, coefficients E0 to E5 for C2, and coefficients F0 to F5 for VOCV. Next, the function form proposed by Chen, where the open circuit voltage, resistances, and capacitances are also only a function of SOC. Coefficients A0 to A2 for RS, coefficients B0 to B2 for R1, coefficients C0 to C2 for C1, coefficients D0 to D2 for R2, coefficients E0 to E2 for C2, and coefficients F0 to F5 for VOCV. Last is the two-dimensional table method that accounts for the effect of temperature. Unlike the previous two methods where the parameters are only a function of the SOC, the parameters in the 2D table method are a function of both the SOC and the temperature. According to the 2D table method, we define the open circuit voltage, resistances, and capacities in terms of temperature and SOC as a structured table. Finally, according to the electric circuit's relations, the electric current in the battery is obtained. Then, the volumetric current transfer rate in the potential equation is computed as shown. After computing the volumetric current transfer rate, the heat generation rate in the energy equation is computed as shown. Last, we refer to Newman's P2D electrochemical model. Unlike the semi-empirical NTGK and ECM models, the P2D model is physics-based. In other words, Newman's group has developed a physics-based model using porous electrode and concentrated solution theories. The P2D model accurately captures the lithium ion's migration inside the battery. So we assume that a battery has a porous electrode pair where lithium ions move in the holes inside it. Porous electrodes are composed of spherical grids where the lithium conservation equation is solved in the R direction. Hence, this model is called pseudo-two dimensions. According to Newman's P2D model, we present a schematic of a lithium-ion battery as shown. Here, the composite electrodes consist of active materials and an electrolyte solution. The solid active materials are modeled as a matrix of mono-sized spherical particles. On the other hand, the electrolyte phase is continuous throughout the negative electrode, separator, and positive electrode. As a result, there are two phases in the lithium-ion battery construction: the electrolyte phase for the lithium ions transfer in the negative electrode, separator, and positive electrode, and the solid phase for the electric current transfer in the solid grids only in the positive electrode and negative electrode. According to the P2D approach, the lithium-ion transport in the porous electrode and electrolyte is described by the charge and mass conservation laws. The lithium conservation equation in the solid phase is described as shown. The lithium conservation equation in the electrolyte phase is described as shown. The charge conservation equation in the solid phase is described as shown. And the charge conservation equation in the electrolyte phase is described as shown. Finally, we determine the source terms in the potential and energy equations. In Newman's P2D model formulation, the volumetric current transfer rate in the potential equation is computed as shown. After computing the volumetric current transfer rate, the heat generation rate in the energy equation is computed as shown. Generally, we can simulate both a single battery and a battery pack in ANSYS Fluent software. Now we intend to describe the battery pack. Battery packs are battery systems in which multiple single batteries are connected in series or parallel. In series connections, the positive terminal of the first battery is connected to the negative terminal of the next battery, and so on. Note that in the series configuration, the current remains constant and the voltages add up. However, in parallel connections, the positive terminal of the first battery is connected to the positive terminals of the next batteries, and the negative terminal of the first battery is connected to the negative terminals of the next batteries. Note that in the parallel configuration, the voltage remains constant and the electric currents add up. In battery pack simulations, all batteries in the pack must have an NPMS connection pattern. That is, N batteries are connected in parallel, and then M such units are connected in series. For example, we consider a battery pack in which 4 batteries are connected in series. In the battery pack, there are 2 ways to connect the single batteries: real connections and virtual connections. The real connections are created by bus bars. It means that the bus bars are physically modeled and considered in the computational domain of the model. However, according to the virtual connections, bus bars' volumes are not explicitly considered in the computational domain. Instead, the connection information is provided by the user in a battery connection definition file. Then, the solver reads this information and recognizes connections between individual batteries. Note that the virtual connection method saves time and reduces the meshing difficulty of the busbar's volumes, which are usually very thin. After a comprehensive introduction to battery model concepts, we intend to discuss the battery model settings in ANSYS Fluent software. First, we turn on the Enable Battery Model option. There are several tabs available in the Battery Model Settings dialog box, including Model Options, Conductive Zones, Electric Contacts, Model Parameters, UDF, and Advanced Options. The Model Options tab contains the general model settings, including battery solution methods, electrochemical submodels, etc. In the Solution Method section, there are different approaches for battery modeling. In the Electrochemistry Models section, there are different submodels for electrochemical computations in the batteries. In the Electrical Parameters section, we specify the operating conditions of the battery. The Conductive Zones tab allows users to select zones for active, tab, and busbar components. In the Active Components box, we select the appropriate zones for the active components of our battery. Active zones are the main battery cells where electrochemical reactions occur. In the Passive Components box, we select the appropriate zones for the passive components of our battery. Passive zones include tab zones and bus bars used to connect the tabs of different batteries. The Electric Contacts tab allows users to define contact surfaces and external connectors. In the Contact Surface box, we can define the contact surfaces involving contact resistance. Note that considering contact surfaces in the battery system is optional. In the External Connectors box, we define the positive and negative tabs or terminals of our battery system. Note, however, that we define external connections when we use real connections in the battery system. We enable the Use Virtual Battery Connections option when we want to use virtual connectors to simulate the battery pack. In other words, if we physically model the battery connections geometries such as tabs and bus bars, it is called real connections. Otherwise, if we do not physically model the connections geometries to reduce the computational cost, we can use the virtual connections. The Model Parameters tab is where users determine parameters for solving the battery model equations. Here we set the parameters related to the battery solution method and the electrochemical submodel. So note that the model parameter settings depend on the solution method and the electrochemistry submodel enabled by the user. Hence, we select different models and then define their related parameters. The UDF tab is where users can apply their user-defined functions. The Advanced Options tab allows users to use various advanced modeling capabilities. Here, a series of optional capabilities and tools are available, which could be used by the user if needed. Thank you very much for being with us. I hope you are satisfied with our training. The Mr. CFD group will always be ready to provide you with training services.